Hello everyone, and welcome back to Mitchell's Physics Review. This unit we're working on energy. Let's take a look at our first problem. A 10 kilogram block is released from rest point A in the figure below. The track is frictionless except for the portion between points B and C, which has a length of 6 meters. The block travels down the track, hits a spring force constant of 2300 newtons per meter, and compresses the spring 0.25 meters from its equilibrium position before coming to rest momentarily. Determine the coefficient of kinetic friction between the block and the rough surface between points B and C. First, let's label our givens from both the diagram and the question. We know the force constant on the spring is 2300 newtons per meters. We know the mass is 10 kilograms. We know the distance the spring is compressed is 0.25 meters. We know the length between point B and point C is 6 meters. And we know the change in the vertical direction is 3 meters. So, if you jump straight into this problem with your LOL diagram, you might see that there's too many unknowns. So we're going to have to start by breaking this problem up and finding the unknowns until we only have one, which is the coefficient of kinetic friction. So to do that, we're going to break it up into finding the equation from position A to position B. So we know that since it's at rest and on top of the lift at position A, all the energy is stored gravitationally. And then we have our system of the mass, the spring, and the earth. And then we know at point B, it's on the flat surface, or considered ground level, and it's moving straight at a constant velocity. So then we can call that kinetic energy. So let's start our equation. We have UG is equal to K. 4 boxes is equal to 4 boxes. Then we have our storage method equations, and UG can be said mass times G times the height equals 1/2 mass times velocity squared. So we can cancel out the masses, and then all we have to do is plug in the numbers. So 9.8 for G, the 3 meters for the H, and then we're going to multiply by 2 to get rid of that half, equals V squared for the B position. So then we get 58.8 equals V squared, and then for velocity in the B at position B is 7.67 meters per second. Now that we have our velocity at position B, we're going to try and find the velocity at position C. So, at position C, it's already past the bumpy surface, so we know all of that energy is stored kinetically. We have the same system, but this time it's compressing the spring. So then all that energy is transferred into elastic energy. So our equation should be kinetic energy equals elastic energy. For that, we can plug in the equations for kinetic and elastic. 1/2 mv squared for position C equals 1/2 k times x squared. From there, it's once again, we're just plugging in our numbers, our mass, our spring constant, and then the distance the spring is compressed. From there, we just solve it algebraically, and we get that the speed at point C, or the velocity at point C, is equal to 3.79 meters per second. Finally, since we have solved for 2 of our unknowns and we only have 1 left, we're able to go and start finally solving for the coefficient of friction. So first, let's do this by setting up an LOL diagram. And we know that at point B, like we said earlier, it's all kinetic energy. We have the same system, but this time, since there's friction, energy is lost due to the floor. So that results in, at point C, the kinetic energy being less than it was to begin with. So for this equation, it's going to be our kinetic energy at position B minus the working done by the floor equals kinetic energy at position C. Next, all we need to do from there is plug in our equations to the storage method equations into our original equation. So 1/2 mv squared equals the kinetic minus the working, which is force times displacement, equals 1/2 mv squared. So then we plug in numbers, and we plug in our mass, we plug in the velocity at position B, the mass, the velocity at position C, and the distance between point B and point C. But how do we get to this coefficient of friction? Well, for this, we're going to have to look over here. We know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So we can draw a little free body force diagram down here and see that the normal force is equal to the gravitational force, which means we can say Fn is equal to Fg, which means and Fg and mg are the same, so we can say Fn is equal to mg. From there we plug in our mass, we plug in g, and we get Fn is equal to 98. So then we know that the frictional force is equal to the coefficient of friction times 98. So that's what we're going to plug in the next step of our equation. For Fk, we're going to plug in mu and then times 98 times 6. From there, it's solving algebraically. So we're going to move this over to the right side to make it positive. We're going to square root, multiply, and then divide each of these portions till we get 150.474 is equal to 588 mu k. We're going to divide by 588, and we're going to get our coefficient of friction is 0.256. Now, overall, through this problem, I learned a lot about using LOL diagrams, how to understand them, how to write them into equations, and also understanding better overall that energy is always conserved. I hope you learned a lot from this video too. Thank you.